In this section, I'm going to talk about how computer networks work. So computer networks are kind of like a phone system for computers, where any computer can place kind of a data call to any other computer. Now, the basic outlines of how it works are surprisingly simple, although of course the details are fairly complicated. But I figure, just making up a statistic, I expect most Stanford students are using a computer network within 10 minutes of waking up in the morning, and probably within 10 minutes of falling asleep at night. So I figure, well, it's kind of worth knowing. So I'll start at the small scale. A LAN stands for local area network. These are very common. A LAN is a network that would be used to cover maybe one floor of a building, or maybe just within a house or something like that. So I'll talk about that case first, and then in the next section I'll talk about how that scales up to cover the entire Earth with the internet. So two very common examples of LAN technology are Ethernet, which is uses wires, that's wired LAN technology, and Wi-Fi, which is the wireless radio, sort of analog to Ethernet. Those are both incredibly common, so those are worth seeing. So let's talk about wired Ethernet first. So the way wired Ethernet works is it uses these wires that are maybe about the size of a soda straw. Here's a picture of one. And they terminate in these jacks. This is called an RJ45 jack, which is a little bit bigger than a phone jack. And here you can see the wires going into it, and the wires are all, a lot of times they're blue or yellow. And Ethernet is good for about 100 meters maximum length. So you can see that's how it sort of covers, basically one building or one floor or something like that. Here's a picture of a wireless router, but just so you can see the two Ethernet cables going into the back. And so if you've got any piece of, a computer or something that you're going to use Ethernet with, it's going to have this kind of plug in the back, and at some point you end up plugging this Ethernet jack in there. So that's what that is. So what I want to figure is, well, all right, so if you have these wires, how is it the data gets from one place to another? So the case I want to consider is, let's say, here on computer 1, I've got flowers.jpg, just a file with a lot of bits in it, and I want to think about, well, how would I send that over the Ethernet cable over to computer 2? So the way that works, the way all networking is done, is that if you've got a relatively large file, the way the networking layer is going to deal with stuff is to break the data into what are called packets. And so each packet is relatively small. Packet might be 1,000 bytes or maybe 1,500 bytes. So I'll use 1,500 bytes. It's a common size for my running example here. So when computer 1 wants to send this image, really what it's going to do is take the image, all those bytes, 50,000 bytes or whatever it is, and break it into a series of packets where each packet is only 1,500 bytes. And so all we have to think about is, well, how do you send one packet on the wire? And then you can see how it sort of scales up. You just send all the packets. So I want to look at the case very specifically of Ethernet sending one packet. I'm going to start on the right-hand side here of my drawing. So let's say I've got your computer 1, and you've got this packet. And if we were to look inside of it, basically it's a series of bytes, where each byte is a series of 8 zeros and ones. So the way this is going to work is that the sending computer, the way you can think of it, is it just reads through the first byte here, and there's just a pattern of ones and zeros. And so it's just going to follow a scheme saying, all right, let's say that for each one, we'll call that 3 volts. And so I'll put 3 volts on the wire. And every time there's a 0, I'll put 0 volts on the wire. And so it just kind of reads through. You don't have to understand electricity to follow along, but it just reads through and puts a pattern of ones and zeros on the wire. And I'll sort of hand wave a little bit, but it turns out the wire, that pattern of ones and zeros sort of travels along the wire here. It'll make the most sense if you just look at the left-hand side and just imagine the receiver is just looking at the wire. And what the receiver is going to see is a series of voltages. So the first thing the receiver sees is like, oh, 3 volts. Okay, well, I guess that's a 1. And then the next thing that it comes, it's like a pipe. The electrons are coming out. The next thing it sees is a 0. Oh, okay, I guess that was 0 volts. And then there's 3 volts. Oh, I guess that was a 1. Oh, it's still at 3 volts, so I guess that's another 1 and a 0 and so on. So the receiver, you can think of just observing this pattern of 3 volts and 0 volts coming down the wire. Of course, it happens very, very quickly. And from just observing the pattern of 3 volts and 0 volts is able to sort of recover what the original byte was. And so ultimately, that's how the entire packet is sent. The sender just reads through all the bits and sends a pattern of voltage. and the receiver basically reconstructs all 1,500 bytes to get the packet back. So that's actually how it works. That's how it is. You could have data on one computer and they're connected with an Ethernet cable, and somehow it like sends all the ones and zeros over that wire. So a natural question is, well, what about errors? So for modern Ethernet, the transmission happens at a rate of 1 billion bits per second, a billion ones and zeros per second on that wire, so very quickly. And it's easy to imagine, yeah, sure, every now and then there's going to be an error. A 1, for some reason, comes through as a 0 or something like that. So I want to talk about this technique called checksums that are just kind of interesting to see and are really used to detect and correct errors. So the way it works is, I'll look at my little diagram down here, is the sender, before they send the packet, they could look at the whole packet, and it's just a bunch of numbers, right? A bunch of bytes, each between 0 and 255, as we know. And so what the sender could do is go through these numbers and just add them up. So in this case, these add to 491. And the sender will say, let's say, we'll just choose as an example. Let's say our scheme is that we just always take the last 2 digits. So in this case, the last 2 digits are 91, and we'll say, that's the checksum for this packet. And so we'll just put that on the end and send that too. So the way this works is that obviously the receiver gets the whole packet, and the receiver can just do the same addition. So the receiver adds up all the bytes that they got, and they see, oh, did they get 91 too? Do the checksums match? If the checksums don't match, then that suggests, well, some bit in there got flipped. There was some error. Something didn't come through quite right. And so what the receiver can do is just ask the sender to resend that packet. Each packet is relatively small, so this is not a big problem. And so the result is, basically this provides a little guarantee that each packet came through correctly. And so by requesting the one is resent, the receiver can eventually end up with a perfect set of packets and sort of having checked each one. So this scheme is used actually not just in networking, but in many layers of computer systems. There's this notion of having a checksum that accompanies the data to sort of make sure that each transfer went through correctly. So that's how it is that you could have some large JPEG file on your computer and put it on a thumb drive and then later send it over the network. And somehow, even though you're sending it from place to place, it keeps coming through really 100% correct, right? Each 0 and 1 is exactly what it's supposed to be, and checksums is a little bit what's going on behind that for that to work. One thing I should mention is that this checksum scheme, well, so first of all, the scheme I described here is just adding it up. The real checksum scheme that's used is a little more complicated than that. But it is possible that you could have 2 errors that sort of cancel out just so there's an error, but the checksum scheme doesn't detect it. That's possible, although it is a microscopic possibility. But this is not a completely foolproof scheme. So I want to scale this up a little bit. Thus far, I've talked about just essentially having 2 computers with an Ethernet cable, and talk about, well, so how does Ethernet scale up to having a bunch of computers all talking to one wire? This is, I think, a nice design to see. It's a very elegant design, and patterns that you see in this design will reappear. It's such a successful design that it's been kind of used for solving a lot of problems. So let me just set up the problem here. I'll look at this picture at the bottom. So the way Ethernet works is that you could have a bunch of computers. So here I've drawn 4 computers, and there's just one wire here, the sort of backbone, and they're all sharing it. So the Ethernet design is all about having one shared piece of hardware and a bunch of computers using it, and they're able to cooperate to use that shared bit of hardware efficiently. So I want to talk about how it is that one computer would send a packet to another computer on Ethernet in a setup like this, where I have a bunch of computers all sharing the wire. So the analogy is always that it's kind of like at a cocktail party, that if you have a bunch of people all sort of facing each other, they're able to have a conversation, even though 2 people can't really talk at the same time, but they're able to sort of cooperate and take turns, basically. And Ethernet works in a way similar to that. So here's how it's going to work. Each one of these computers has an address, a unique address. So I'll say, computers 1, 2, 3, 4. And when a computer wants to send a packet, so here I've drawn on the left here a packet, the packet will begin with a 2: field. It'll say, what is the destination computer for this? So let's say in this case that computer 1 wants to send a packet over here to computer 4. So computer 1 will get the packet ready, and then what computer 1 will do is wait for a period of silence on the wire. So maybe computers 2 and 3 were having some conversation, so the wire was kind of busy carrying that traffic, but eventually the wire goes quiet. And so when computer 1 hears a period of silence, then computer 1 puts the packet on the wire, sends it out there. And naively, you sort of think, oh, well, it's like the packet sort of goes down here and turns right, goes to computer 4. But really, it's more like a broadcast. The signal of that packet just spreads out on the wire, and it just spreads out to every corner of the wire. So it's really a broadcast. It just occupies the entire wire. Now, the way it works in Ethernet is that every computer is listening to the wire all the time. Everybody listens to the wire. And what they're doing is really they're just listening for packets addressed to them. So when this packet addressed to computer 4 goes out, computer 4 will hear it and say, oh, hey, that one's for me. And so copy down the zeros and ones for that packet. Like, okay, that one's for computer 4. And computer 3, computer 2 will also see the zeros and ones going by, but they'll just notice, oh, hey, 2 colon computer 4. Okay, that one's not for me. And so they can just disregard it. So that's how it works. So the interesting case for sharing with Ethernet is, what if computer 1, as I described before, is going to send a packet to computer 4, but it happens that computer 3 also had a packet to send. And if they're probably, if you're just unlucky, it's possible that both computer 1 and computer 3 will hear the same period of silence. And so they will both decide to start sending on our one shared wire. And so what will happen is the wire can't carry multiple conversations at once. And so if they both start transmitting, there's said to be a collision where the two conversations kind of overlap and they overwrite each other, and it eventually just becomes hopelessly garbled. So both packets are basically destroyed and useless by this collision. So what happens is, ideally, both computer 1 and computer 3 eventually notice that someone else is talking over them, and so they can at least stop transmitting. And so the wire gets back to being quiet. And so both computer 1 and computer 3 realize, like, okay, well, that didn't work. So if they both just heard the silence and just started transmitting again, well, it would just collide again. And so this is a very clever part of Ethernet, which is, well, how to get them essentially to take turns, right? To get one to transmit and the other one to wait. So the way this works is that both computer 1 and computer 3 in Ethernet wait a random amount of time. They just make up a random number and say, well, I'm going to wait that long, and then I'll try and transmit. And so in effect, it's kind of fair. In effect, one of them will end up going first. The wire won't be quiet anymore because it's carrying that conversation, and so then we can just go back to our regular strategy. So that enables that when you get a collision, essentially they both sort of back off, and then one of them is able to take turns. So eventually you're able to use the wire pretty efficiently. So that's how you have a bunch of computers all connected to just this one Ethernet wire, and they're able to use it pretty efficiently. Now, probably most of the people watching this aren't maybe using wired Ethernet anymore. That almost seems like a little bit old. The very common way to connect to any kind of network now is Wi-Fi. And I'll tell you, I'm going to talk about Wi-Fi very little. It's really the same strategy. So the hallmark of Ethernet was that you had this shared wire, and only one person really can transmit at a time, and you want to kind of somehow collectively share it. Wi-Fi is exactly the same. In this case, instead of a wire, what you have is a radio channel. So there's some radio channel that's being used, right? So we've got all these computers. They have little radios on them. I've drawn these kind of lame radio transmitting marks on here. So there's some radio channel. They're all sharing it. And then it looks very much like Ethernet. So they're going to have a strategy of waiting for a period of silence, and when there's silence, broadcasting. All the computers listen all the time, watching out for packets addressed to them and ignoring packets that are not addressed to them. And sometimes you'll have a collision. Two people start transmitting at the same time. You want to sort of notice that, and then have some random back-off strategy so that you can wait for silence again and transmit without overlapping. So it just happens. Very similar strategy works. So just to kind of to summarize, as I was saying, some of the qualities that go into Ethernet's design reoccur in sort of larger problems. It's just a fundamentally a bunch of good decisions, and so I think it's worth seeing for that reason. So the setup is that you've got the wire, the radio wave, or whatever, some shared resource, and you want to use it efficiently. And the solution is not going to involve a central authority. Instead, all the actors are going to have a distributed and collaborative strategy. So they're able to cooperate with each other collectively to use the thing efficiently. Another quality, which I'll point out now, which I didn't point out then, is this is very insecure. Remember like when computer 1 was sending a packet to computer 4? Well, that packet kind of went to computer 3 too, right? If computer 3 wanted to listen in, they could. This really gets back to the notion of, well, what does shared mean, right? Shared in this case means when anybody broadcasts, anybody else can listen. Not anybody else on Earth, but anybody else, within 100 meters, sort of on that same local area network. And so that is certainly true. Now, this doesn't mean that all security on the internet is hopeless. It just means that there's another layer of encryption and security that we would want to add, that the LAN itself is not secure. And so I'll talk about that more when I talk about it in a later security section. Another quality of this is that because you've got this one medium that you're sharing, it means that as more and more computers are using it, the performance available to any one computer kind of degrades. And again, this just gets back to sharing, right? Well, if computers 2 and 3 are tying up the wire with some, sending some big file or something, well, that means that there's going to be less silence. And so computer 1 will sort of get fewer bytes that they're able to send. That's not, it can be a good quality. What you want is that the performance sort of degrades. You get less capacity, but it doesn't just break outright. And so Ethernet definitely has that quality of degrading. So as I said, it's a very popular, very successful set of design choices. And so we'll see that kind of thing later on.